the reason we have these engineering approaches to solving these real-world structural problems is because we've determined and demonstrated now rather conclusively that elasticity theory is hard, right? It is something that's very difficult to solve in a sort of back-of-the-envelope, closed-form analytical solution. And so we find these engineering approaches, such as beam theory, that's one that we're talking about last lecture and this lecture. We find these to be incredibly useful for simplifying the problem, for providing us a tool set and mechanisms and approaches for thinking about the problem and how to solve it. And that makes our elasticity theory something that we can actually apply for real world structures like aircraft and spacecraft. And so that's what we were doing. And we developed last lecture the kinematics of the Euler-Bernoulli beam. Recall, we described the Euler-Bernoulli beam as being something that is much longer in one dimension than the other dimension, and the loads that are applied to it also have to be consistent with Euler-Bernoulli beam theory. And one of those requirements is that we have to be able to treat the loads as resultants at points along the beam reference line. And so usually that manifests itself as being a integral over the cross-sectional area where we would either have an axial load, a transverse shear load, or a bending moment about one of the two bending axes of that beam structure, or alternatively a torque. So if we're able to do that, we were able to develop beam kinematics. Again, what's kinematics? Kinematics is the description of how it bends, how it deforms. And we did that based on looking and watching how it deformed. And by observing certain things about that deformation, we made some simplifying statements and assumptions. We wrote down equations that quite accurately represent the deformation of the beam. And then last but not least, of course, the final piece of the puzzle is that because we now have equations which describe the deformation, we can take derivatives and calculate strain. And taking derivatives is much easier in general than integrating. So we can take derivatives of that to get strain. From strain, we can calculate stress. From stress, we ultimately can go back and calculate these resolved or resultant loads on the cross sections. And the whole process of solving the beam equations is much easier than solving the complete elasticity solution. So at the end of last lecture, say about the last 10 to 15 minutes of the lecture, we demonstrated calculating the resultant force, the axial resultant force on a given cross section, which we found out was, of course, just the integral over the area of the cross section of the sigma ZZ component of stress. And what was kind of interesting about that is by choosing our coordinate system at the centroid, we actually determined that the axial resultant load is only related to the stretch of the reference line, also known as the strain of the reference line. So that was really kind of neat, kind of interesting, very powerful. That brings us up to speed here, and now we can pick up at the bending moment calculation. So just to remind you where we are and what we're doing, you know, we had a beam and, you know, we could sort of draw a beam. It's much longer in the x-axis here than it is in the y or the z-axis. We have, of course, the reference line. We've taken a cut, so we're looking now at a cross-section of the beam. That cross-section now, as you project it in this example, is essentially a square cross-section.
Sir? We can't see a screen if you haven't shared it.
Thank you.
Thank you.
All right, so you haven't missed anything yet because it was just jabber up till this point. Now, this is really the first slide where I had anything meaningful. Except for the announcements, but I spoke all the announcements, so you guys heard them. Anyway, so we have this cross section, Again, here's my beam. I'll just redraw it, rehighlight it one more time. So along the x-axis here, this is the horizontal axis, we had a reference line, which is kind of this dashed line that I've drawn in here. If we looked at a cross section of this beam, in this example, the cross section is just going to be square, although it does not have to be square for the purpose of our calculation. Now, keep in mind, we were able to, with our beam kinematics, describe the deformation of the beam as being something related to the strain of the reference axis. That's what we're going to call epsilon zz0. Minus now the x position within the cross section times u comma zz, and the y position within the cross section times v comma zz. Again, x and y are just defined up here in this image, always measured relative to the centroid, which in this case is in the center. And these terms, just to remind you, u comma zz and v comma zz were curvatures of the beam about the corresponding axes. Okay, the first derivative is the slope, the second derivative is the curvature, and strain is related to the curvature, and stress is related to the strain. So sigma zz is simply the modulus times this quantity. And of course, if we're calculating bending moments, we need to then write an expression for bending moments. So I'm going to give just a few seconds here for you to think about what an expression for bending moment about this axis would be. So we're looking for an equation for moment. And I'll give you a hint, it's going to have an integral in it, just like we had for the resultant force in the axial direction. Okay, I'm not hearing anybody volunteer, so I'll give another hint. Again, it's going to require an integral, and here I've defined dA, a differential area within the cross section, and we note a stress at that location, dA. So I see Scott has volunteered in the chat window the integral of y times the stress with respect to the area. Very good. We're getting pretty close actually here. So the resultant bending moment about the centroid, we're going to call this mx, so it's about the x-axis. It's the integral over the area of y, that is the distance from the reference axis to the point where dA exists. So y times sigma zz dA. Why do we need both of those? Well, what's a moment? A moment is a force times a distance. So you can think of this term in here as being a differential moment. So we're integrating a differential moment over an area. Differential moment is the moment arm times the stress at that point. So very good. Thanks, Scott. Of course, we can then complete that integral. We recognize, well, what's dA? dA here is nothing more than dx dy. So that integral now becomes this integral. By the way, I should have, yeah, so I mentioned dA, and we'll return to that in just a minute. But because we know what stress is, we can take this whole equation here, and all we need to do is then plug that in here, and that's the first thing that I've done. And the next thing to take note of is that the terms within sigma zz, not all of them are functions of position. We'll look at the first one, notably the strain of the reference axis. Again, the reference axis here, the reference line would be at the center. No matter where you are in the cross section, the strain of the reference axis will always be the same. So that's a constant. So that gets pulled outside of its integral. The y dA term still lives on the inside of the integral. I've pulled the modulus. You know, modulus was outside to begin with. I've pulled it outside completely. So strain is constant with respect to the area. U comma zz, v comma zz, those are curvatures of the reference line. are going to be constant with respect to the area. It's the same argument we made last lecture. So again, that can come outside the integral. That can come outside the integral. What remains inside the integral is anything that is now a function of dA, which is really a function of dx and dy. So y is now a function of y. xy is a function of both x and y. Y squared is now also a function of y. We note the y squared comes from y here times y here, so that's where the y squared comes. Xy comes from x and y, so that's where xy comes from. Okay, now again, going back and just briefly looking at these integrals, we've seen these integrals before, at least some of them. So just to remind you, the integral of y dA was equal to 0. This is by choice of the coordinate system. This is because we created our coordinate system at the centroid. That is, in fact, the very definition of the centroid. If you're forgetting the details of that, go back and revisit your notes from last lecture. The integral of xy dA, we're going to define this as a term. Okay, so we're going to call this IXY, two subscripts, IXY. It's the area product of inertia. Area product of inertia. The next one, the integral of y squared dA, we're going to define this one as well. We're going to define it as IXX, the area moment of inertia about the x-axis. Now I want to highlight something that's a little bit different about our treatment of IXX. So in my notes, I am calling this IXX. I am maintaining two subscripts on the I. That, for me, it's just clearer to me what that means, because then the double subscripted XY and the double subscripted XX both have the same number of subscripts. However, in the textbook and in probably most textbooks, this would just be called IX. Okay. So I'm preferring sort of symmetry about the notational scheme to the single reference to the x-axis. But if you see IX, recognize that IX and IXX are the same. One is from my notes and one is probably from somebody else's notes. It's also worth noting that the value of IXY is going to be equal to 0 if and only if there is symmetry about the XY axis. No, I got to step back. Not if and only if. I'm just saying if there is symmetry about the X or Y axis. There are actually other special circumstances where that integral will be 0 when there is not symmetry. So pay attention to that. My if and only if statement was inaccurate. There is a special circumstance where we can actually intentionally drive IXY equal to 0 and learn something about the cross section. But we'll defer that for later discussion. Okay. Actually, this little bracket indicates what I was referencing there. If there is we can drive that to 0 to transform into a principal axis of the cross section, sort of like we calculated principal stresses. I guess the last thing I need to say to caution you about, let me go back to the equations we were looking at here. So we were able to pull this E out, the modulus out, because we were treating it as constant with respect to the cross section. Okay, this statement here, the one that's the circled equation, is true, irrespective of whether E is constant. But when you put E inside the integral and then integrate with respect to A, we can only pull it out if E is not a function of X or Y. Therefore, again, we have to be careful. If E is a function of X and Y, then it must remain inside the integral. And ultimately, when that happens, we don't have a real clean separation between material properties and sectional properties, or properties of the cross section. These terms here, these integral terms and the results that they, the I values that are computed, those, when E is constant, we can now call those geometric properties of the cross section. However, when E comes inside, then we can't, like I said, we can't use the combination of a constant modulus or a non-constant modulus and IXX in the same way that we could if it's constant. Now, details of this are important. We actually hit it very heavily in the composite materials course. And so if you're interested in that, that's another class that I would advertise for your graduate program if you decide to stick around here at WMU. All right, I'm looking over. I see a question from Nicole. She says, what is the difference between area moment of inertia and area product of inertia? Like, which one is 1/12 BH cubed for a rectangle? So great question, Nicole. Thank you. It's this one here, y squared dA IXX. This is the one that becomes 1/12 BH cubed for a rectangle. The other one, and we're going to get to this later, but since you asked, I will certainly highlight it right now. The IXY term, when it is non-zero, okay, it is zero sometimes, but when it is non-zero, this ends up being a coupling term between bending about one axis and bending about the other axis. Okay, so that's the big answer. That's the most important answer. Of course, the much less useful and straightforward answer is simply that the integral is defined with different terms, and so therefore it will have a different value. But the big one, the most important thing to take away would be this coupling. Now, I will return to that in a future slide where we actually see the equations that illustrate the coupling that occurs, but that's not present in this slide. I hope that answers the question. If not, certainly continue to ping me in that chat window. Okay, so we have completed the calculation where we calculated the bending moments about the y-axis. I'm sorry, the x-axis. Now we will start the calculations for the bending moments about the y-axis. So this figure that you're seeing on this slide is very similar to the one that we drew previously. However, now the x and y axes are flopped. So now it's x up instead of y up. That's a slight difference. We still have this differential area dA, which of course is equal to dx times dy. We still have a stress at that point. We still have this same stress equation given by our derivation of the kinematics last lecture. Once again, if we compute the bending moment resultant about the centroid, we have to do an integral equation. So here it is. The moments about the y-axis are going to be equal to minus the integral over the area of x times sigma zz dA. Okay, notice the convention of the minus sign here. We'll address that later. For the moment, just accept that the minus sign is present by convention in this calculation. And like we had previously, here is our moment about y calculation now. So here it's the integral. Now we have a minus sign, minus e times these quantities. These quantities are slightly different in this example. or in this calculation, this is an x instead of a y. We get an x squared instead of an xy, and we get an xy instead of a y squared. Now, I saw out of the corner of my eye Scott's question. Scott asks, does it matter that the axes don't follow the right-hand rule? And the answer is that is where the negative sign comes from. The way I've drawn it is with the axis, the y-axis to the right, but in reality, we're going to have to flip the whole thing around if we wanted to make it positive, but that kind of begs a slightly different question, and it can be confusing that way as well. So this is the way I chose to draw it, and then to highlight the fact that we need the negative sign. So that's good insight in your question there, Scott. Thanks for asking. Okay, moving forward, of course, just like previously, we have this, that is the integral of x dA is equal to 0 by choice of coordinate system. The integral of xy dA is still called IXY, so that's identical to our prior calculation. And last but not least, we have this integral of x squared dA is, by definition, our area moment of inertia about the y-axis. Note, I see here that I have a typographical error. There's supposed to be a y here. And just like I stated for the IX or IXX value, I've chosen to use two subscripts, although most textbooks only use one, IY versus IYY. I like the visual consistency. Although I admit maybe the visual consistency is not entirely accurate with regard to what other people are doing. And again, likewise, if we have IXY will be 0 if there is symmetry about the x or y axis, and these arguments are identical to what I had on the prior slide, so that's not something that needs to reside here for very long. I do want to be a little bit conscious about not moving too quickly. So if I'm moving too quickly during lecture, if I'm advancing a slide too fast for you to be able to capture that information, please feel free to interrupt me. Okay, so here on this slide now, I've written those equations in their summative form. All right. This is the outcome of the integral. Let me go back a couple of slides just to make sure you're seeing directly where this is coming from. So here we had this equation, my is equal to minus e, parentheses, epsilon z0 times this integral minus u comma zz times that integral minus v comma zz times that integral. Now I've completed those integrals. I've substituted these values for x dA, xy dA, and x squared dA, and the end result is this equation. Or I should say these three equations, really. The two equations are the moment equations. Note the centroidal coordinate system allowed us to get rid of the term that had previously been there. That's the stretch of the neutral axis, or I should say the stretch of the reference axis. All that remains now in these equations are the terms that didn't go to 0, that is IXY, which can sometimes go to 0, and IXX, IYY, and IXY, which again can sometimes go to 0. Okay, so this form is now easier. We do have to be careful and recognize that the mx by convention has the minus sign in it. That's to account for the right-hand rule that Scott had alluded to. The my has the positive signs by our convention that we're going to choose. Really, this convention is the convention about, which way are we calling moments? Are they sort of smiley face moments such that bending creates a positive moment, or is a smiley face moment a negative moment? We've chosen one, and that's resulted in this convention for the signs. And last but not least, I've added to this collection of equations the one that we derived last lecture. That was that the resultant force P was nothing more than EA times the strain of the reference axis. I divided that by A here, just kind of for kicks. So here we see that this is the average sigma ZZ stress is what sigma PP over A, I'm sorry, P over A is. Sigma ZZ is equal to P over A. Now what we have is we have three equations that define the loads that are applied in beam bending problems. Now, in our lecture that we did yesterday, 2 days ago, I said that beams carry axial loads, beams carry transverse shear loads, beams carry torques, and beams carry moments. Now, we're not dealing with the torque part. We're going to get back to that in a subsequent lecture, because that's twisting about the long axis of the beam. And I promise we will get there, and that'll be very interesting as well. But we have now done all but the shear of the other loads. We have the moment loads, we have the axial load. So what is not present in these equations explicitly is the shear loads that are present on the resultant of the cross section. And I will be dealing with that later today. So hold on, we'll get there. Here's the really nice thing. Because we chose our centroid as our reference axis, we had additional terms that go to 0. That was ultimately the term that was related to epsilon ZZ0. It doesn't show up in the moment equations. It does show up in the axial equation, but what we're finding here is bending and axial stretch are decoupled. I'll say it again. Bending and axial deformation are decoupled in a beam if we choose that correct coordinate system, the centroidal reference line. That's a really key thing, and one of the things that makes beam calculations, in fact, quite simple to do once you get used to them. It's also worth paying attention to the fact that we are able to invert and solve this equation. What I mean when I say that is here we have on the left-hand side what starts to look a lot like a vector, mx, my. We have u comma zz and v comma zz, which ultimately this can be written as a vector with a matrix times a vector. And here the u and v comma zz is here. So you'll see this written in this matrix form in upcoming slides. And when I say we can invert and solve, we can directly invert this matrix and move it over to the other side. All right. Any questions before we move on? All right, I'm not hearing any, so we'll go ahead and proceed. So the next thing we're going to do is we're going to begin to express these findings, these beam equations that we're developing. We're going to express them now in terms of differential equations. And I think that'll become clear what I mean by that in the next few slides. So we'll start again with axial loads rather than bending. Here is so here's a beam, okay? In this case, the cross section of the beam is no longer constant. So none of the things that we're talking about require the cross section to be constant. Okay, so in this case, the cross section is actually tapered, so it's a little bit narrower. Then it gets a little bit wider. We can take a free body diagram by taking a cut on each side. So we're going to include the entire beam height and width in our cut, but we're only including a small portion of the axial length of the beam. And we know that we can have a resultant on the negative face, and the corresponding arrow is pointing in the negative direction. So that's going to be we're talking now in the stress sense. It is a tensile force, which is positive on a positive face or negative on a negative face. And note that we're going, again, the z-axis is the long axis of the beam. So the little differential cut we took was of width dz along that axis. So we've got a normal resultant P on the left side at position Z. We've got a normal resultant to the right, P, at the position Z plus dz. And last but not least, conceivably, there could be a body force, something like gravity, that's acting on this in a volumetric sense, pulling it off to the right. So in the axial direction, again, we've defined, this is the definition. I'm going to expose a little bit more of the wording here. Give me just one moment. I'm going to have to pause here for just a second. Okay, I apologize about that. I'm back. Okay, so again, by definition, this is just the way we're naming our variables. P was the overall resultant force in the axial direction, and we're going to now say it's a function of z. So P with z in parentheses. I'm now going to describe a new term that we haven't yet seen. This is the distributed axial load. So this is that body force that I have right here in the middle. It is a body force like gravity pulling the differential element to the right along the long axis of the beam. Now what's important to recognize here is that we're going to describe this in terms of force per unit length. Force per unit length. So the units on the distributed axial load in beam theory is force per unit length. Now, why does that matter? That means that if it were actually gravity, the units need to work out. So rho A is a density per unit length times gravity would give us a distributed load per length of the long axis of the beam. Now note, this is very much directly related to the stress equilibrium equations. However, we have to be careful when we expressed it in terms of body forces per unit volume in the stress equilibrium equations. The units on that body force were different. That was force per unit volume. This instead is force per unit length. So similar, directly related, but different in our unit convention. Of course, lo and behold, what are we going to do with this? We have to apply equilibrium. Okay, most of this course in one way or another is applying equilibrium. So what does equilibrium mean in this context? Well, it's pretty simple. The sum of the forces in the z direction is equal to 0. Okay, we're assuming this beam is not accelerating, although, certainly we could include acceleration if we needed to. Given that we're assuming quasi-static, we only need to track these contributions. Well, what pulls to the right? That is P at Z plus DZ, and our body force per unit length. So we have to multiply that by DZ. Note the positive sign in this equation. So this one's positive and this one's positive. Well, what acts in the opposite direction? That is P as a function of Z. So that one has a negative sign. Okay, lo and behold, 0 is equal to this. P at Z plus DZ minus P at Z. I've divided that whole equation by dz to get rid of the dz that was previously here. Okay, so after division, it now is in the denominator. And now this term here starts to look quite familiar to us. I assume you guys know what that is. Anybody wants to, they can throw it out. Yep, Ethan got it. It's a derivative. Here it is. So in the limit, again, this is a limit argument. In the limit as dz becomes small, this becomes a derivative. So dp dz is equal to, we subtract this, we move that onto the left-hand side. So dp dz is equal to minus little p of z. As a general rule, this can be a function of z. So we have to maintain that notational scheme. We don't want to assume it's a constant. Okay, now, just to remind you of what we had concluded previously, we said that the overall resultant force on any given section was the average stress times the area, which we could express as EA times the strain of the reference axis, which of course the strain of the reference axis was defined as the first derivative of the W displacement of the reference axis, again times EA. Herein we're saying E and A are constants with respect to the cross section, although they are not necessarily constants with respect to the Z axis. Now I can take that and I can plug it into our now derived differential equation. I'm going to show the rest of these, so if you guys are writing it down, you have a little bit of time. dp dz can be a function of z, is now equal to, and we're just subbing in EA dw0 dz into the p, and now it's going to be equal to the right-hand side. So this is interesting. So here is our, this is really the big hitter here. This is the important equation. D by dz of EA dw dz is equal to minus little p distributed load as a function of z. I stated that we didn't have to assume that E and A were constant. The cross-sectional area can change. If it changes as a function of z, it has to remain inside this square brackets. Similarly, if E is a function of z, it has to remain inside. But for many of the problems we're going to do in this class, just to make it a little bit easier, I might assign properties such that E and A are constant. And if that's true, then they can be pulled outside of the derivative. And what you end up with is just EA times the second derivative of the stretch of the reference axis, second derivative of the displacement of the reference axis, I should say, is equal to minus the distributed load. Another thing to take note of is if this right-hand side is 0, what do we see? We see that the axial force does not vary. Okay. If it's 0, then this axial force is a constant. If there's no gravity acting, it's a constant. Now, in your homework that's going out today, or went out today, you're going to be addressing this equation. So that's a hint for the homework. Note in the problem, it's actually a variation of the problem that we already did in homework set 4, which is why I partially released homework set 4 solutions already. We want to pay attention to the fact that in that problem, the distributed axial load is not 0. So we would therefore have a non-constant P. So that's some hints for the homework that's coming up due next Thursday. All right, before we move on to the next topic, do we have any questions about the axial governing differential equation for beam forces? You guys are awful quiet. Confirm at least for me that you're still hearing me, please.
We can hear you.
Wonderful. Okay. Thank you. All right. So we're going to now move on. What we have described now over the last, say, 4 or 5 slides was the axial equilibrium equation, the governing differential equation of axial equilibrium. Let me go back for one moment. This is a differential equation because of this term here. It's the second derivative of the axial length, axial displacement, I should say. I see a question came across the chat window. So Ron asks, so for little p, the force is changing as you travel down the z direction. So that's possible. Little p can change. Again, this is the amount of axial per unit length body force in that z direction. So little p can change as a function of z. In fact, it will in your homework set. That's why I'm giving you the homework that I gave you, is to wrestle with that idea. And it's that spinning bar, right? So when you have a common, maybe one of the common areas where this actually shows up is in problems where you have something spinning about an axis, a beam or a rope or something spinning about an axis. So that's because the centrifugal force is now a function of the radius. P becomes a function of the radius. The right-hand side is a function of the radius. Now, I don't think that that is entirely what you were asking. Maybe it was. But the other point to make, of course, is that P, the big force, capital P, if little p is non-zero, big P, therefore, is changing as a function of z. Okay, so getting started now on this slide. Here we have bending static equilibrium. I've done that same thing that I did last time. So again, we have this beam, right? And I took a differential cut, a cut on the left-hand side, a cut on the right-hand side. The length of the cut, the difference between the two cross sections in the z-axis was a length dz. So here's our dz length. I'm just representing this now as a line rather than representing the whole cross section. But I think otherwise this is not going to be confusing. Now, when I say we have bending static equilibrium, really you can think of this as transverse loads rather than axial loads. The last few slides were about axial loads. Now we're looking at transverse loads, so loads across the beam, and there are a couple that are present. So in general, we could say there is a distributed load. Much like we had a distributed axial load, we could have a distributed transverse load. And on the faces, the cross sections of this beam, we can have shear loads, shear load resultants. So what we're doing here is we're taking the sum of the forces in the x direction, which is composed of the distributed load plus the shear loads in the x direction. Like we previously had, we have it at Sx, z plus dz, positive on a positive face, Sx at z, negative on a negative face, and last but not least, pz, which is going to be positive by our definition. So what are these things? So what we're showing here on this particular slide is Sx, although in general you could have Sy if we were looking at a different axis. We have Px, that's again a distributed lateral load. Once again, we think of this as a force per unit length. The units on it should be written in force per unit length. And then last but not least, of course, we've already expressed bending moments, and we're going to bring those back to the forefront here in just a minute. Now, one might ask, what's Px? How do we, what could cause Px? Again, gravity would be a very good example. If you've got an airplane wing, the wing itself weighs something, and the weight of it pulling down on the wing is now a distributed force along the length of the beam, where in this case we're calling that wing a beam. Yeah, it could be, so gravity is, I would argue, perhaps the most common, but of course, that's not the only one. Certainly aerodynamic loads, if we're generating lift on a wing, that's going to create a bending, a distributed bending load as well. Just like we did with the axial forces, this is the same diagram. Just as we did with the axial forces, we can sum the forces. In this case, we're summing the forces in the x direction on this differential element. And that's pretty easy. In fact, what I will, the way to express this is simply the, in the positive direction, we have Sx at z plus dz plus the distributed force Px times dz. So those are the positive things. We need also a Sx at z in the negative direction. And for some reason, as I converted from my older format, we're missing a term in this equation. I will correct that and then, of course, upload these into the electronic course pack again later in the day. But, this is the same thing. So we had Sx at z plus dz, and then minus Sx at z plus Px dz is equal to 0. So all of that should live in there. And then, of course, when we divide by dz, this just becomes the derivative. Dsx dz is equal to minus P of x. So on this slide, I've made another minimal change. I swapped the x and the y axis, so now we've got a y here. Our forces now are y. And, there's no rocket science to this in comparison to what we had last time. We're just deriving a new equation for this sum of the forces in the y direction. So now dsy dz is equal to minus py. Okay. Any questions on that? No? In fact, let me go back just one more time. We're going to stare at this for one more second. What do we have? We have now an equation, much like we had. I see Brendan's asking to go back one more slide, and I certainly can. Is it this one that you wanted? Let me, I'm going to clear away some stuff here so that I can circle this term here. So I see David says, can you please use orange instead of blue? It's hard to see. Okay, so that's a good point. Thank you. I will do that next lecture. I can't make that switch in real time here. So here, we had an equation dsx dz is equal to minus px. We had another equation dsy dz is equal to minus py. Again, what do we find here? Much like we observed with the axial load and the axial resultant force, what we're seeing is the shear resultant force in each of these two directions. Its derivative with respect to the z-axis is now a function of the distributed load in that direction. Okay, that's true now in both axial direction and the two transverse directions. All right, now, so what have we done? We've done now 3 sets of equations. We have done the sum of the forces in the z direction. That was the axial loads. We did the sum of the forces in the x direction. That was transverse. We did the sum of the forces in the y direction. That was transverse. Here we're now going to apply moment equilibrium. And I've got a diagram that now includes, it's the same cuts that we took before. We still have the shear resultant on the positive face, positive direction. We still have the shear resultant, negative face, negative direction. We still have the distributed load. But now, since we're calculating moments, instead, we actually have to include moment resultants on each of these faces. Now, the shears themselves contribute to moment, so we have to track those. In our previous calculations, the moments do not contribute to the forces, so these were neglected previously, but here we need to track them. Okay, now in this diagram, we see we're defining it such that the moments, as I've drawn them, if we have a positive moment, it will cause the beam to deflect in such a way that it makes a smiley face, and smile up, edges up rather than down. So that is our convention for positive moments about the y-axis. Okay, if the x-axis is drawn up as I have here. Now these equations, not terribly difficult, right? They're similar to what we did before. I'll start with the things that contribute positive moments, and then I'll subtract things that contribute negative moments. So if we're positive counterclockwise, so moments that are counterclockwise are positive, positive face, positive direction, negative face, negative direction. What we see here in the moment equilibrium is, and I'm just going to shorthand this just a little bit. So my of z plus dz, I'm expressing as my plus dmy. And so that's what this one is going to be expressed down here. That's going to be positive since it's counterclockwise. This one is negative because it's clockwise. So we subtract off minus y. What else contributes to the moment? Now we need to define the moments about what point. I'm going to choose the center, so I'm going to make that dot blue. There's a reason we choose that. You guys think of why that might be while I start to address then the next term. That is the shear resultant. So the shear resultant on the right-hand side, I'm expressing it as Sx plus dsx. On the left-hand side, that's this one over here, that one is Sx. Note each of those are equidistant from our reference point. So they are, to convert those forces into moments, we need to multiply by dz over 2 because this length is 1/2 of dz to get to the center. And it's worth paying attention to the fact that even though this is negative face, negative direction on the left-hand side for Sx, it contributes a positive moment because relative to our reference point, it is generating a counterclockwise moment. So the S's all add together. I can manipulate this equation just a little bit. And since I'm subtracting my from my plus dmy, on the left-hand side, we get a dmy. I'm moving everything to do with s over to the right-hand side. So dmy is now equal to minus 2sx plus dsx times dz over 2. I anticipate you guys are well able to anticipate yourself what's coming next, and that is, of course, to divide by dz. So this is just the last equation. You already wrote it down. It's worth noting that in the limit, as dz goes to 0, ds also goes to 0, and this essentially disappears. Then, of course, I divide by dz. Actually, I'll divide by dz over 2. So what we end up then is 2 dm dz is equal to minus 2sx. We cancel the 2's, and we get this differential equation, dmy dz is equal to minus sx. Okay, are there any questions on that? Now, you guys may be wondering, why are we doing this? Why are we spending all this time going through and calculating these, not terribly difficult equilibrium statements? The reason is because we're ultimately deriving our beam equations, the governing differential equations of beam deflection. We had written moment equation terms before, but we didn't deal with how moments change as a function of position. So now we're actually expressing how moments change as a function of position. And oh, by the way, in doing so, we now highlight that last load type that I had referred to at the beginning of our beam lecture. That is the reference, resultant loads, which are either the moments or the shear resultants or the axial resultants or the torques. And we're going to defer the torques till another lecture, but we've now done everything but torque. Okay, we did that with respect to the y-axis previously. Now we can do it with respect to the x-axis. This is a very similar argument, so nothing really exciting about this slide. We want to pay attention to the fact that, just like we saw earlier, because of the right-hand rule arguments, we're going to have a sign convention difference between that one and this one. So in this case, we're going to say that we have a positive sy rather than a negative sx. So I'm going to flip-flop back and forth. Here's the last slide. dmy dz was minus sx. But if we do this calculation, again, identical to the last calculation with respect to everything but the sign convention, we get a dmx dz is equal to positive sy. Okay, so in summary, what have we found? We applied equilibrium really there 4 times. We did some of the forces in the x direction. We did some of the forces in the y direction. We did some of the moments about the x-axis. We did some of the moments about the y-axis. We expressed now 4 equations from those equilibrium statements. dsx dz is equal to minus px, dsy dz is equal to minus py, dmx dz is equal to positive sy. This is the one kind of outlier, weird one with the different sign convention. And dmy dz is equal to minus sx. We, of course, recognize that the Sx and Sy terms here are the same Sx and Sy terms here. I see a question on the chat window. So Amir asks, so for the equations 11 through 14, the terms on the right-hand side are all resultants. Well, no, not exactly. So this is a resultant, that is Sy. This is a resultant, that is Sx, because both of those are integrals over the area. These terms here, and I'm going to box them because I want to identify that they are different. These are not resultants. This is, remember, a distributed load. That is a load per unit length in the transverse direction. So these are loads that cause bending. In this case, load per unit length in the X or the Y direction. You know, as I said, Sy here is the same as Sy up there. So ultimately, we can therefore manipulate, combine these equations. So those four statements of equilibrium can be simplified into just two statements of equilibrium. That is, the second derivative of mx is equal to minus py, and the second derivative of my is equal to plus px. So although the S does not explicitly live in these equations, S, the shear resultant force on the cross section, it's present. It is present because of these equations up here. So it's kind of masked a little bit, but it is present. Okay, on this slide, we're looking at the equations that we derived previously. This is now on the order of 30 minutes ago in lecture. I mentioned at that time that we can express them as a set of matrix equations. So here I've actually done that. Be a little attentive to the fact that we have xy's on the diagonal term of the matrix, and the ix and iy, which I'm using double subscripts xx and yy there on the sort of off diagonal terms. And that's really nothing more than collecting terms with respect to uzz and vzz. I mentioned 30 minutes ago that we need to be able to do the matrix inversion. I'm sure you recall from prior courses, maybe even high school mathematics, or perhaps even before, how to do inversion of matrices. We have a 2x2. This is a 2x2 matrix, so you have this formula that is pretty well known. Basically, you swap A and D, so D moves and A moves, and then you negate C and B. So B stays in the same place but gets negated. Same with C. And then in all cases, you divide by the determinant. So so this ends up being D over AD minus BC, and so on. So all that's real simple stuff. You've done it before. So all I'm doing now is inverting those matrix equations that were present previously. So I swapped A and D, I negated B and C, and I calculated the determinant. And in this case, the determinant is going to be equal to this term here. We see a product of x and y, and then we get an ixy squared. And each of those has, effectively e squared present in it because it's ei versus ei squared. So, that's what the determinant is. And, lo and behold, now we have, what do we have? This is actually a pretty critical equation. Okay, it may look rather innocent, and matrix inversion of a 2x2 is nothing special. But as we stare at this equation, what do we see? Well, we have on the left-hand side an expression for the displacement. Now, it is the second derivative of that displacement, but it is the beginnings of an expression for the displacement. This is the amount of deflection that beam undergoes as it's bending. What do we have on the right-hand side? Well, we have something that relates to the geometry, that is E and I, and the material. So E represents the material, I represents the geometry, and then, of course, the right-hand side vector, mx and my, is the load. So this column here is load. This column here can be thought of as, sort of compliance, really, is what it is. I was writing stiffness, but this is compliance. It's a matrix term, and it represents the material and geometric, so mat plus geometry. And then this over here, as I mentioned, was displacement, second derivative of it, but important. Okay, so now everything's starting to make a little sense. It actually isn't too difficult because the 2x2 matrix is really easy. You guys can integrate, the integration Ix, Ixy, Iy, those were all pretty easy area integrals to do, no problem. And of course, in the last 3 or 4 slides, we finally related these moments to the distributed load. So here we're going to go ahead and deal with that in another couple of slides. Should check the time. We have about 5 minutes left. Okay, so by the way, if you're making a formula sheet for the exam, if I give you that as a option to use during the exam, I would say you pretty much better have this version of the equations on it, or alternatively, you could have this version of the equations on it, assuming that you can do inversion of the 2x2 without having to think too hard about it. Okay, this is just a remembering. Remember all is what I was going to say. That's like from Harry Potter. Recall. This is a little brain reminder that stress was equal to modulus times strain. Now here in this context, because we are decoupling the bending from the axial load, I'm not paying attention to the axial load in this problem. I've only got the bending terms. But so stress was equal to E times this is what we would call the stress curvature relationship. So U comma ZZ was curvature, V comma ZZ was curvature about the other axis, and X and Y are distance from the neutral axis. We plug in all these terms that we have now calculated, and lo and behold, we can say that, here U comma ZZ was equal to, here's U comma ZZ. So it's equal to 1 over the determinant of EIXY times MX plus EIXX times MY. Similarly, we had the V comma ZZ term, which if we went back, we could look at that. V comma ZZ is the second row, 1 over the determinant of minus EIYY times MX minus EIXY times MY. Therefore, wow, stress is really easy to calculate. Okay, so between the second derivative of displacement, which allows us to calculate displacement, and stress, we're really easily able to compute deflections, strains, and stresses from the applied geometry, material, and loads. Okay, now, last but not least, here's what we have. Again, if you want to box equations, if you want to have equations that are ready to go for a formula sheet, or if you want to memorize equations, these are the equations right here. Boom. This is the big deal. Now, what's different between this version that I am putting in the box now and the prior version that was these equations? Okay, actually it was these equations over here. Okay, here we have moments. This is the moment to second derivative relationship. Moment to second derivative. But going back a few slides, here was the moment to applied load relationship. And you can see here we had a second derivative of moment is distributed load. So second derivative of moment is distributed load. Moment was equal to second derivative of the out of plane displacement here. And when you combine those two things, and I recognize I'm flipping through slides, so hopefully you're able to capture all this. If not, I'm happy to go back. If we take the second derivative with respect to z of the moment, that's what this was, the moment inside of here. Now we're taking its second derivative and setting it equal to the distributed load. Second derivative of moment is equal to distributed load. Second derivative of moment is equal to distributed load. Say that in your head 10 times. It's a really good thing to sort of tattoo on your brain. Note also that we can sometimes simplify this even further. But before we do that, I will also highlight one other thing, that because of the sign conventions we've used, and we had a couple of places, there were two places where we had minus signs kind of show up where we thought they were somewhat non-intuitive that they did, but it was because of that right-hand rule that was referenced by one of you guys in your questions. Now, because we had it twice, the minus signs have canceled, and these equations really are the ones you should remember, and oh, by the way, they're positive. Okay, another thing to keep in mind here is really two more things to keep in mind. I'm going to highlight one of them first. Recall we said if there was symmetry about the x or y axis, IXY was equal to 0. Okay, I'm going to draw a cross section for you. Now pretend my artistic ability is outstanding, which it's not, but let's pretend. Here is an XY axis. If we have a square cross section, it's symmetric about, in fact, both X and Y. Okay, we could have a triangular cross section. That one would be symmetric about Y. We could turn that triangle on its side. That one would be symmetric about X. In any of these three examples, there is symmetry about one of those two axes. IXY goes to 0, and when that happens, then this form of the equation shows up. This one is decoupled. That means that the displacement or deflection in the u direction is not related to the displacement or deflection in the v direction. And really, when I say u direction, I'm saying in the Cartesian x direction, that displacement, we call it u. If and only if IXY is equal to 0, these bending equations are decoupled such that bending about one axis does not impact bending about the other axis. Okay, now I said that is true if there is symmetry. We also can, if there's a non-symmetric cross-section, we can choose a convenient coordinate system to drive IXY to 0 and have decoupling, but that would rarely be in the sort of nice, convenient Cartesian XY system that we've laid out so far. Okay, but again, decoupling, uncoupled equations. Anytime something is uncoupled, uncoupled differential equations always much easier than coupled differential equations. Okay, and I guess last but not least, this is the same equations. Now it's just written in moment form rather than being written in second derivative of moment form. Anyway, but what we have now, mx is equal to minus EIXX v comma zz. So this is decoupled. It's direct moment curvature relationship with decoupled axes. Okay, we have reached the end of our allotted time for the day. And I'm seeing that one or two students have already kind of scooted out. I was thinking maybe we should do one quick example, but for the sake of time, I think we'll just defer that until next Tuesday, especially since students have scooted out so quickly already. I'm happy to stick around for a few minutes to take any questions that you may have. Otherwise, I'll see you guys next week. And it's worth noting that what we're doing now is not likely to be on the first exam. So when beam theory starts, that's kind of where our first exam ends, even though the exam is not for a couple of weeks. That's the beam bending calculations will not be on that first exam. So I'm seeing a question. Well, let me answer Nicole's first. So she says, can you explain where the last two equations come from? Yeah, sure, happy to. So the last two equations actually come. They're not new equations. In fact, we've already used them. It was these equations here, Nicole. Except now if we say that IXY is equal to 0, there and there, what we get is that MX is equal to minus EI XX V comma ZZ and vice versa. So MY is equal to EIYY U comma ZZ. So not new. We're just canceling a term that if it is 0, it simplifies the equations. All right.